Good morning. It is GCSE season, so students are preparing for exams. I've had a student ask me to review some topics in magnetism and electromagnetism for the GCSE spec. Go away, cat. Right. So the specific topic he's asking me about is it's, I suppose, comes under the motor effect. It is specifically to do with Fleming's left-hand rule. So if you're not familiar with Fleming's left-hand rule, that would be where you use your left hand, you've got a thumb, you've got a pointing finger, and you've got another finger, which people often do rude signs with. So that's like your fist. And essentially you use these three fingers to represent three things. So the motion the direction a wire might move in a magnetic field, the direction of the magnetic field, MFC, and the direction a current is flowing. So that on its own might not make sense. So let's put it into a bit more context. We are talking about maybe a situation where you have a horseshoe magnet, which is a north-south magnet sort of bent round on itself. I'll try and draw it 3D so you get an idea of space. Okay. Now in between the north and the south poles, we imagine there are field lines. Okay. So these green arrows here represent the field lines, and when you're using Fleming's left-hand rule, your pointy finger will represent the field. So you align your pointy finger with the field, and then if you put a wire, if you put a wire in between the in between here, and you show the direction the current is flowing through the wire, and that's conventional current, positive to negative. So if I was to have connected this wire up to a cell, the cell side positive would be on this side. Okay, so the current is flowing in a loop around the wire and back. So I would now, let's get the colours to represent the bits we're talking about. I would get the current is flowing this way through the magnetic field. So you would align this finger with the current. You'd align this finger with the field, and if you do that, your fingers should be telling you that the motion of the wire will be up. Right, I should do that a different colour really, shouldn't I? So the motion of the wire, I'll do as purple here, the motion of the wire would be straight up. So that's the motor effect. Basically, when you have a wire experiencing a force, because it's got a current flowing through it and it's in a magnetic field, you'll get a force. Right? So that allows us to make motors. If you loop this wire around, so if I was to have exactly the same setup, a north-south magnet. So I'm going to draw it slightly differently here, north-south, and another magnet here, north, south-north, right? Field lines would be this way. If you put a loop of wire in here and you had a cell, right? This side the current will be flowing this way, this side the current will be flowing that way. Again, I can use Fleming's left-hand rule to quickly check which way the direction will be. Again, I will use purple to represent motion. So there is no shortcut to any of this business. You have to get your hand and line it up and look at which way you think this is going to move. So I get my forefinger and I point it in the direction of the field. So that would be this way. My forefinger is pointing that way. I get my my sweary finger, sort of my middle finger, this one, and I point it in the direction of the current. So in this situation, on this side of the wire, the current is in this direction. Right, that tells me that this wire here gets pushed downwards. Right, so the motion on this side would be down, and if I flip the current to come out of the page towards me now, which is like flowing this way, this side of the wire gets pushed up. So you get a turning effect. You get one side of the wire. If you look at this sort of side on here, you'd see one wire sort of going into the page, with current going into the page, which is represented as a dot. One side with the wire coming wrong way around, sorry. and a wire with current coming out of the page, which is what this represents. And that would tell me, using again the left-hand rule, as I've just worked out, this side would be pushed down, this side would be pushed up, and they're rotating about a central axis. So remember your moments. You get a torque or a moment being produced, a turning effect. So as you can see, it'd be very useful for motors. But specifically, the question I'm being asked about today is, what is this formula? What's it all about? Where does it come from? And why should I bother? Or why should I be interested in it? So this is one of my favorite bits of physics. Take something which is really hard to measure and make it measurable. Okay, so that's what we're going to think about here. So imagine you want to test or write down the strength of a magnet. You're a salesperson, you're selling magnets, okay? Hey, buy my magnets. In fact, go on eBay and get the neodymium magnets. You can get some really dangerous magnets. They'll smash your fingers to pieces, right? So to me, that's actually quite exciting, right? But you know what salespeople are like? They always try to rip you off. So they say, my magnet is the strongest magnet you can get. How are they going to tell you the strength, right? Are you going to say, my magnet can bicep curl more than your magnet? That's not exactly, a sensible way of measuring it. If I tell you my car is 900 brake horsepower and weighs 800 kilograms, you can get a good idea that that thing is going to be fast, right? And it's meaningful. So I want to be able to sell you a magnet and tell you the same kind of thing. And in the formula that the exam board have got you to learn and expect you to know, I'm pretty sure you have to learn it. So I'm pretty sure this is not... Oh, it is given on the equation sheet, so you don't have to memorize this one. But you certainly need to understand it in context. So in that formula, you've got force is equal to B times I times L. B is magnetic flux density. Okay, so in non-physics speak, it's how strong the magnet is, how strong the magnetic field is actually. Okay, I is the current in amps, so it's current in amps. Symbol is I. L is the length of the wire in between the field lines. So it will help if I sketch it out, right? So you start with a magnetic field. So imagine we have a magnetic field here. We have a wire, and the current is it flowing into the page or out of the page? The cross, like a bow and arrow. If you see an arrow going away from you and you're looking from this end, you're watching the crosshairs or the tail feathers going away from you. That's the cross notation, tells us it's going into the page. I can use Fleming's left-hand rule, align my first finger with the field, align my middle finger with the direction of the current, and it tells me that this thing gets pushed down. Okay? Right. So what this formula is going to tell me is the size of that force that it's pushing it down with, the strength of the field in between here, right? The amount of current flowing through this wire, which will be the current in amps, and then if I should go back to this black. If this wire is, say, 2 meters long, then that value is what that value is, the length, right? Okay, but let's see how we get that. Let's see how we end up with that formula and how we test it. So that's what the formula is. It's pretty straightforward to apply. You just plug the numbers in that you're given in the question, and you're away. But I think it's helpful to have some context, so to understand how, for instance, we might measure the magnetic field strength in an experimental setting. So that's where we look at something called the current balance. So the idea is you have a top pan balance, which is a scale basically, which measures things in grams. But basically, if you're measuring something in grams on Earth and you know the strength of gravity, weight equals mass times gravity. So if I convert this into kilograms and then I multiply by gravity, I can get the force in newtons. The weight is the force in newtons. So it's possible to use a top pan balance as a force measuring device. Okay. Now on top of my top pan balance, what I will do is place the magnetic field, or the horseshoe magnet that I want to test the strength of. So this is the horseshoe magnet that I'm sketching on here. Okay. Bad drawing. There we go. Something like that. Right. North, south. Field lines would go this way, north to south. Okay. Right. So I want to find out how strong is that B. Okay. So if you were doing it in a sort of useless way, trying to measure the field strength, you might try getting a magnet that you already know, like a test magnet, sticking it to the horseshoe magnet, using a Newton meter to pull it off, which is essentially a spring in a box, and saying, right, that one took 20 newtons to pull off this magnet, right? Can you imagine the difficulty then? Say you're on eBay trying to buy yourself some super strong magnets, and one seller is using a test magnet that is really, really strong, so that they get really high readings, and another seller is using a different test magnet that's a bit weaker. Every seller would need to use the same magnet for you to be able to compare. So this method's not going to work. So what we do is we know that when we do this setup, right here, this business, that the more current you have, this one, let's use a different colour pen, the more current you have here, the greater the force. In fact, you kind of can do it straight away just from experience or from messing around with the equipment if you ever set this stuff up, that if you have a larger current, you'll have a larger force, right? It's also true that when the current in the wire and the magnetic field interact, that if you have stronger magnets, right, it makes sense that the stronger the magnet, the stronger the force, right? And if you've got a certain length in the field, if you only put half that length, so again, let's have a look at this diagram here, or redraw it again really quickly. I keep drawing the same diagram again and again. But if you put just a loop of wire into it and it's only that length, or if I extended that loop and made it longer, right? So if I doubled that length now, that having twice the length in the field, twice being as much being pushed, that bit was being pushed by a certain amount, that bit was being pushed by a certain amount. When you double it up, when you double the length, you'd expect the force to also double. Okay, so these things shouldn't be a surprise. So since we can anticipate that force is going to be proportional to current, force is going to be proportional to the magnetic field strength, force is going to be proportional to the length, we could set up a formula. Just ignore that little bit for a second. But we can definitely anticipate that force is proportional to current, force is going to be proportional to length. So we could say force is likely to be proportional to current and proportional to length. And if you've got both these things changing at the same time, if I double the current and double the length, then that's actually the product of those two things that it would be proportional to. Right? If I want to change that symbol from being a proportional sign to an equal sign, I need to put a constant in there. F is equal to a constant times IL, right? In this case, that constant is going to be the magnetic field strength. It's the one thing we're going to keep the same in the experiment. So, you could do a setup like this. If I've got a wire in here and a current is flowing, say, that way, or this way, let's do it this way, because I think that will be the right way around. Current coming out the page. Quickly just check with left-hand rule. That means the wire gets pushed up, right? Now if you push the wire up, Newton's third law says that if you push something, it pushes you back. If A pushes B with a given force in a given direction, then B will push A with the same magnitude of force, but in an opposite direction. So if you're pushing the wire up, then the wire will push the magnet down. Right? So you've got a Newton pair of forces here. So as you increase the current, you expect the scale reading to increase. From the scale reading, we can calculate the force. Right? So you can do a experiment whereby you have this thing set up with maybe a variable resistor, a cell, right? So you can vary the current flowing through the device. Obviously you'll need an ammeter to measure the current. Right, so imagine you're recording some results. You could record the force, you could record the current. Force would be in newtons, current would be in amps, right? And you could also think about varying the length, right? So if you were to get some readings for a force of 1 and a current of 1 and a length of 1, if that was the truth, if that's what you got, you would expect that if you made the current double and kept the length the same, the force would double. If you went back to the original current and you doubled the length, you'd still have double the force, right? If you doubled both, right, you'd expect to get twice the force from the current, and then doubling the length would double that again, so you'd end up with 4. Okay? You'd end up with 4 on this one. Okay? Now if you plot a graph of force, which is essentially comparing this thing with y equals mx plus c, y equals, right, there's no plus c here. This would be our x, that would be the m. There's no plus c, right, because there's no plus here. There might be a plus c actually, because you could have an intercept. So we've got y equals m times x, and this is the constant, and I times L would be the x, right? So if I plotted force against IL, 1, 1, 2, 2 times 1 is, so I'd better put I times L here as well. Oh, I'm using up, getting squished. Right, I times L in this box. 1 times 1, 1. 2 times 1, 2. 1 times 2, 2. 2 times 2, 2. Oh, sorry, 2 times 2, 4. Yeah? So I can plot this column and this column, right? Which is essentially doing the same thing as I just said, comparing y equals mx plus c to this formula, F, the constant, IL. But remember, the constant is going to be the magnetic field strength. So I'm going to plot force against I times L. For a force of 1, I get a current, I get I times L of 1. So it's somewhere like this. 2 is 2. 2 is 2 again, right? 4 is 4. Right, so you get a straight line. But imagine I redo this experiment now with a different brand of magnet. Whoops, with a different brand of magnet. I get myself a super duper strong magnet. How much stronger? Right, so there's mega more field lines here. Well, I could go back to this method of showing off how strong my magnet is. But as we said, you wouldn't buy a magnet on eBay based on some guy telling you that my magnet's the strongest magnet in the world because it takes 1,000 newtons to pull this thing off, because you don't know how strong this magnet is, right? Or what they're using. But if you get them to repeat this experiment in this new magnetic field, right, you might find, for instance, that, let's repeat the experiment. So we've got IL, L, this should be in meters. That's going to be meter amps, right? Try and stick to the labeling conventions. Amps, length in meters, current in amps, and force in newtons. So if you had a much stronger magnet that was genuinely stronger, then when you had an I of 1 and a length of 1 meter, right, I times L would still be equal to 1, but the force might be much higher, maybe twice as high, right? When you try doubling the current and keeping the length the same, I times L is 2, but this time the force is twice as big because the magnet twice as strong, okay? When you double both of them, and this is 4, this time the force is twice as big because the magnet is twice as strong, right? And if you plotted this on this graph, the gradient would be twice as high. The gradient of this graph is the one thing that stays constant in the experiment when you're changing I or L and measuring force. It's the independent variable. Sorry, it's the dependent variable. It's the thing we're measuring. Oh, hold on a second. Which one's the dependent variable? Independent variable, dependent variable. What's dependent here? Oh, the force is the dependent variable, isn't it? Yeah. Force is what I'm measuring. and I times L is what I'm changing. And the constant in the experiment, the thing that stays the same in the experiment is B, right? So the gradient of this graph being very big for a strong magnet and smaller for a weaker magnet, right? So again, the formula you're given by the AQA is F equals BIL, okay? B, when rearranged for B, is equal to F over IL. And you could find this experimentally by setting up an experiment called the current balance, whereby you vary the variable resistor to vary the current flowing through this field. Okay, you'd obviously have to clamp this in place and hold the wire in place. When the wire experiences a force due to the motor effect, which you can predict the direction of using the left-hand rule, that force will be proportional to the current. It will be proportional to the length of wire that you've got in between the field lines, and it will also be proportional to the magnetic field strength. And if you plot a graph of F against I times L, the gradient of the graph will be B. Okay, I think that's enough information to have a feel for what this formula is all about, and hopefully this wasn't too confusing, although I have to say I've maybe explained it better in the past. So give me your comments and thoughts. It should all be helpful anyway. And by the way, I think that going through the specification piece by piece like this and talking it through and explaining it is a really valuable and useful way of revising. And you as a student need to be checking the spec, really. Definitely when you get to A-level, it is the way our most able and most capable students are revising and getting their head around the information they need to know for their exams. Okay, thanks for watching. Hope this has been beneficial.